Hello everyone, let's try to solve some LeetCode today. So today we have this find peak element problem, that is LeetCode 162 problem, and this problem is at a medium level even though on a first glance it looks really simple. If you really look at it, it should be in the easy problem category, but it is still in the medium problem category. So why is it, right? Let's try to read the description and see. So we have a peak element is an element that is strictly greater than its neighbor. So basically any element in the array is a peak element if it is greater than its left neighbor or its right neighbor. So basically we will have a peak element which needs to be greater than its left and right neighbor both. It cannot be equal to them. It needs to be strictly greater than right and left neighbor. So we have been given a zero index integer array nums, and we need to find the peak element and return its index. If the array contains multiple peak elements, return the index of any of the peak. Great. So basically in the nums array, we can have multiple peak elements and we can return the index of any peak element we want. Great. That's a very simple thing, right? Now you may imagine that nums of -1 and nums of n is equals to negative infinity. That is okay. That's a very interesting condition, right? We might not understand what it is right now, but it's really interesting and important. In other words, an element is always considered to be strictly greater than a neighbor that is outside the array. Okay, that's really important point. So after reading the problem description till now, we can make a few conclusions. Basically, what we want to do is we will have some kind of an array 1, 3, 7, 5. Okay, and we need to figure out a peak element. Peak element is what? Suppose x is a peak element, then x is greater than its left neighbor and x is also greater than its right neighbor. So here which element is actually greater than its left and right neighbor? This element is greater than both 5 and 3. Okay, 7 is a peak element. Well, is there any other element? No, because 5 is not greater than 7. Similarly, 3 is also not greater than 7. 3 is greater than 1, yes, but it's not greater than its right neighbor, that is 7, so it's also not a peak element. Similarly, 1 is also not a peak element because 1 is also not greater than its right neighbor. So at first glance, this is really simple, right? All you have to do is just take the array 1, 3, 7, and 5 and simply run a loop, for loop that runs from I is equals to 0 till I is less than n, that is nums dot length, right? I plus plus. And here all we have to do is we have to check, if nums I is greater than nums I plus 1 and nums I is greater than nums I minus 1. So basically this is the condition that we need to check. If the nums I is greater than its right neighbor, the nums I plus 1, and if it is also greater than its left neighbor, we say, or we basically return I, right? Because the first peak element that we found, we can simply return its index because we can return any index of the peak element, right? So this is kind of simple, right? All you have to do is just run this for loop and it's pretty much the same. See through some edge cases like if the I is 0 and if I is n minus 1. But you can do that easily, right? Overall, it is a very simple problem, right? The time complexity currently is order of n because if the peak element is present at the end of the array, you will actually have to go through the entire array anyways, right? So at worst case, it is order of n. So why is it placed at medium difficulty? It should be at easy difficulty, right? And the reason is this. You must write an algorithm that runs in order of log n. So we cannot write an algorithm that runs in order of n. So it means we cannot just go ahead and run this for loop and just figure it out. It is not going to work. So that is why it is a medium problem. We have to figure out a solution that actually runs in order of log n instead of n. So this is not an accepted time complexity. We have to get log of n. So how do we do this, right? And so based on all the common algorithms that we know, which one actually gives us order of log n time complexity? It is binary search. Yes guys, this problem is actually a modified binary search problem. And here these conditions, nums of -1 and nums of infinity is important. And also there is one more condition in the constraints. Okay, this is at the end of the question. So it is very easy to actually miss this thing. Here what we are saying is that nums I is not equal to nums of I plus 1. Basically what we are saying in this condition is that no two elements or no adjacent elements are going to be equal. No adjacent elements will be equal. Okay. So this is a very important condition and we will see why. So now the question is, how do we solve it with the help of binary search? Well, before we try to apply binary search here, let's try to understand what binary search is. Okay. So if we have an element array like 1, 2, 3, 4, 5, What binary search does is it actually, suppose that we want to find 4. Okay, so what does binary search actually do? What we do is we actually take a left pointer, we have a right pointer. What we do is we figure out the middle. Okay, so r plus l whole divided by 2, right? This is going to give us a middle point, right? And then we check if at this middle point what we wanted to find is it actually present, right? So right now we checked it, it's 3, it's not 4. So what we do is we basically figure out in which space do we have to search here now, or do we have to search here? Which is the space in which we can actually find our answer? That's what we are doing in the binary search. We are basically dividing the search space into two parts. One part will have our answer and one part will not have our answer, right? And right now we are doing it based on whether the given element, that is target, is greater than the found element or middle element 3. Since the target is greater than 3, we know that it can only exist in this side, so we take this half of the space or search space. But at the end of the day, binary search is just to get the half space, or basically to split the search space into two parts so that we can actually ignore all this space easily. That is basically what we have to do in this problem also. Here we can actually have an unsorted array 1, 3, 7 and 5, right? Now we want to actually break this into two parts. One will actually have an answer and one will not have an answer. So how do we do that? Because it is not a sorted array. So we can do this with the help of a few observations. Okay, this is what you have to do in binary search problems. You have to make a few observations. Suppose that you get the middle as 3. You figure out the middle, r is here, l is here, mid, suppose you got 3. Okay, now first what we will do is we will check, is 3 greater than its right parent and its left parent? Since we can see that yes, 3 is greater than its left parent, so this is correct. But 3 is not greater than its right parent, so here the condition fails. So we know that 3 is not the element that we are looking for. But how do we figure out now whether we should search in this half of the array or in this half of the array? This is where the observation skills comes up. So now that we have 3, if we actually go towards this part, we will be going towards an element that is smaller than 3. Clearly, this element clearly cannot be a peak element because this element itself is smaller than its right neighbor, right? So it means the 1 will anyways not be a peak element. Now if we go towards 7, this side, we see that this 7 is greater than this 3. So yes, half of the condition for an element to be peak element is fulfilled. That is, this particular element 7 is greater than its left neighbor. Now yes, we still don't know whether the 7 is going to be greater than its right neighbor or not. We don't know yet. But suppose that it's not greater than its right neighbor. Okay, suppose we actually create a new array 1, 3, 7 and 10. We came here, okay, we rejected this space, this part is rejected, right? Now we move towards the 7 and here this condition is true. We already know that 7 is greater than 3, that means 7 is greater than its left neighbor. Now if 7 is again smaller than its right neighbor, then what we do? Because here the condition is failing, 7 is not greater than its right neighbor. So what we do is we shift. So if we again shift it towards this side, the bigger side, we get an element that is greater than its left neighbor. So 10 is greater than its left neighbor, and right now we are at the end of the array. So we have this condition here. So we have this condition here, that is nums of -1 and nums of n are in negative infinity. An element is always considered to be strictly greater than a neighbor that is outside the array. So it means that at this point there might be, we are only considering that there are some element outside, and we are directly saying that this 10 is going to be greater than whatever is outside. Okay, there is no element outside, but we are just saying that if it's at the end of the array and we have a smaller element here, we have 10 here, so we are automatically saying that okay, this 10 will be peak element if it's only greater than its left neighbor, because we are considering that yes, it will always be greater than its right neighbor. It's greater than its right neighbor because 10 is at the end of the list. Think of it like this. We have a few points here, okay, at different peaks. We find a middle point, okay, and then we see, should we go here or should we go here? This is the question, right? If we go here, we know that this particular element is not going to be peak. Now, if we go here, this element can be a peak because it actually solves half the problem. Now, if this element is not peak, right, if its next element is greater than this element, what we do is we again shift this side. Since we get to the greatest element, it will eventually be peak. Now you might have a few cases like this: 1, 2, 3, 7, 5, 10, right? Now, if we go to the 3 as a middle element, we shift towards this, we go to the 7, yes, we found a peak element, right? But what if this was opposite? We had 7 in place of 5 here. So 5 was here, 7 was here, right? You go here, you reach 5. This condition is satisfied that 5 is greater than its left neighbor, but now again the 5 is less than its left neighbor. Now what you do? Simple. You shift again, you reach 7. Okay. Now this is again greater than its left neighbor but less than its right neighbor. You shift again and then you reach 10, right? So 10 is definitely going to be greater than its left neighbor, right? Because we already saw it. And it is going to be considered to be greater than its right because there is nothing on the right side. So it's automatically greater than its right neighbor. So what we are doing is we are trying to figure out a condition in which we will surely find some element as a peak element. Can we find a peak element in the remaining search space? Now please understand one thing, okay? Yes, we are trying to figure out the solution here. We are dividing the search space into two parts. But what we are doing here is we are not saying that this part or whatever we are remaining or throwing away is not going to contain an answer. Okay. For example, if we actually choose the middle point to be suppose 5, 5 is definitely greater than its this parent, right? But it's less than this parent. Now we should go towards this side because we are sure that we will find some kind of peak element. But it does not mean that we cannot go towards this side. If we go towards this side at this point, we will eventually find or reach at a peak element 20. Okay, this is always a possibility. But what we are doing is that we are going towards this direction because we are 100% sure that we will find a peak element at this side. Here we can find it, but we are not sure. That is why we are actually removing it this space. Of course, if 3 was at this side, 7 was at this side, we would be going towards this place. We would be searching on this side. So we are basically choosing a search space in which we are definitely sure to find an answer. We are not leaving anything to luck. So here I have coded the solution. First of all, I'm taking the left pointer L, then I'm taking the right pointer R, that is nums.length minus 1, simple. Now we are simply running a while loop until the left pointer is less than or equal to right pointer. In the while loop, first we get the mid index, that is the middle, then we try to get the right element. If the middle index plus 1 is greater than nums.length minus 1, it means it's outside the array. What we do is we simply get the minimum value present for long derive. Otherwise, we simply get the nums mid plus 1. Similarly, for left element, if whatever middle we got, if mid minus 1 is less than 0, it means it's outside the array again. What we do is we again assign the minimum value that we can to this element. Otherwise, we simply assign nums mid minus 1. And here we are checking if the middle element right now is greater than left element and the middle element right now is greater than the right element. We simply return the answer mid because it is a peak element, so we can directly return it. Otherwise, if it's not true, what we check is if the mid element is less than left element, R will change to mid minus 1. So we basically shift the R pointer towards mid minus 1. And if it's not true, otherwise, if the mid is actually less than the right element, that means the right element is greater than mid. So we simply shift the left pointer towards mid plus 1. And at the end, here I'm returning 0 because we have to return something from this. We know that eventually we will find an element that is going to be a peak element, but we have to return something at the end, so I'm just returning 0 here. Like we will never reach this code because we will always find a peak element here, so we will always return from here, but we need to have this return just so that we can build the solution, and that's it. Now let's try to run this thing and it works. If you have some problem that you would like me to solve, then just let me know in the comments. Bye.